So the new 2D Pyro Solver node is finally available, and I'm very excited to share this thing with you guys because I've made some pretty big updates. When I say updates, I mean I've rebuilt the entire solver from scratch this time, following the same structure and the same techniques used in Houdini's top level Pyro Solver. So this should be pretty much as close as you can get to Houdini, but inside Blender. And all these things you're seeing here were the tests I did earlier today with my 2D Pyro Solver. I'll just let this play out for a sec. Nice. So in this explainer video, I'm going to be breaking it down into 8 parts so that you guys can get comfortable with the solver, so you know how each step works, because it can get a little bit complicated in certain areas. And I want to make sure you guys have this kind of instructional video, so if ever you need, you can go back and watch the part that's specific to you, so you can have clear instructions on how to use the solver. So first of all, these are some of the updates that I've included in this version of the solver. So we have newer and more advanced advection schemes, including upwind, single stage, and McCormack advection. I know these are big fancy words. You probably don't know what they mean yet, but don't worry about it. I'll explain it later in the video. We also have trace mode options, including single step, trace RK2, RK3, RK4, and CFL adaptive trace. We also have vortex confinement, in other words, vorticity preservation. We also have multi-step non-divergence projection, so that's good for better collision detection and volume preservation. And then we also have custom attribute inputs for a float attribute and a vector attribute. So in part 1 of this video, I'll show you how to import the nodes into a blend file and create a very basic setup. So that's going to be the nodes that we're going to import, and this is going to be the basic setup that we're going to create, just a circle with a blowing smoke to the right. In part 2, I want to show you the advanced settings, and this is important because this solver is really flexible, so you can either make it run really fast but kind of low quality, or like with basic systems, or you can make it really high quality, really complex systems, but it's going to be a lot slower to simulate. So if you understand the advanced settings, you can balance out the settings to get the kind of result that you want. And yeah, so first we'll go over the project non-divergence steps, then we're going to go over the velocity and field advection methods, then we're going to go over the trace modes, and then we're going to go over the well, some of these settings, the custom float and vector attributes. In part 3, I'm going to show you how to create a wind tunnel simulation, so we can go over the wind force, and this is going to be really fun because it's just fun. You know, everybody loves to see a good wind tunnel simulation, some aerodynamics simulation, and you can plug in your own collision objects. You know, do like an F1 car or something, add some wind and stuff. So in part 4, I'm going to show you how to properly source attributes, and this is a really important step because it's a little bit complex with my solver, because I wanted to make it possible so you can have multiple objects with different initial velocities and different colors all interacting with each other. So there you go, that's an example. So you can see I have 2 sources. One is blowing smoke to the right, one is blowing smoke to the left, one is blue, one is red. Yeah, I'll show you how to do all that. In part 5 is the most boring part. I'm going to show you temperature and buoyancy. It's pretty much the same as my last solver, so I'm going to keep this really quick and simple. But we'll just yeah, go over these shaping settings and the buoyancy settings. In part 6, we're going to do a quick little particle advection, so I'll show you how to transfer velocity from our grid to a bunch of points. So this is a particle advected simulation. In part 7, I'm going to show you how to advect UV attributes using the solver, and this is going to be pretty important as well, because what you can do is simulate kind of low quality, like a basic level simulation, and then use the UV attribute in your shader to advect a high quality image. So you get like high quality looking smoke, but it's actually a very basic smoke sim. You're just advecting the UV attribute. So this is just a screenshot of what advecting the UV looks like in the viewport. And then finally, part 8 is the part you've all been waiting for, the velocity field trickery. I don't know what to call this, but the drippy that I released on my Instagram not too long ago. The whole point of the Pyro Solver was to be able to do this in Blender. Yeah, so there you go. Let's start with part 1, importing the nodes and creating a very basic setup. So here I am with a brand new scene in Blender. The first thing we have to do is append the geo nodes into this blend file. So we'll go File, Append, and you can locate where you saved the Pyro Solver blend file. Go inside, go to Node Tree, press A, press Enter, and now we have the geo nodes in this blend file. So now we can create our basic setup. We can start by creating an object. It doesn't matter what the object is, because we're going to go straight to geometry nodes and create a new node tree, delete the group input, and we can press Shift A and search for Pyro Solver. There it is, a big fat node with a bunch of sources. tabs, because I wanted this to be as organized as possible. So right now you're not seeing anything, and you're also getting an error up here. It says attribute doesn't exist. Don't worry about it. It's just because we don't have a grid plugged in. So let's get a grid, plug it in. Now, for those of you wondering, can you plug in something else here, like for example a sphere? The answer is no, you cannot do that. And well, it's because when you're simulating smoke in Blender with MantaFlow, you have to have a domain, and the domain has to be a cube. It's the same thing in EmberGen. If you're simulating smoke in EmberGen, you have a domain, which is kind of a cube shaped. That's just the way smoke simulations work. They work in a 3D grid, but because this is a 2D solver, it's not a 3D grid, it's a 2D grid. That's just, again, that's just the way smoke simulations work. If you want to kind of create a smoke sim and wrap it around a curved object, you're gonna have to bake out the texture, the smoke data, and then kind of project it back onto another object as like an image texture or something. So here we have a grid, and you can make whatever size you want. You can add a resolution here, so this determines the resolution of your actual smoke sim. And if you want, you can also have irregular sizes, so I can do 2 by 1, for example. The only rule is that your subdivisions are perfect squares. So right now the rectangle, so that's not going to work. So you could do it, mathematically. If this is 256, this would be 512. So that works. Or you can keep it simple. If this is 2 and this is 1, you can do 200 by 100. And if you want more resolution, you can just do a subdivide mesh. And now you have more resolution. So for now, let's just get rid of this and go to a grid of 2 by 2. We'll do 256 by 256. So when you're dealing with a smoke simulation, you're pretty much always visualizing the density attribute. So let's get a viewer node. And if you just do shift, right click and drag, you can get a reroute here, plug that in, get the density field, plug it in, and then visualize. And if I go solve view, we just have black because we don't have any sources. So let's create a source for the density. I'm just going to go and create a sphere, make it a bit smaller. You'll notice when I create the sphere, we lose our viewer. So just click on the grid, click on pin, and then you can go and view your viewer. And now we can click on the sphere and not lose anything. Just move it over here to the left, make it a bit smaller. Now, when you're adding in an object to be sourced, it kind of has to be a 3D object because it's going to say whatever point is inside our sphere is going to have density. So keep that in mind. So we have this sphere, and then to bring it in as a source object, you can do a node called obj to SDF. And this is going to allow you to pinpoint, select your object, and then plug it in to the density. And something's happening. It's kind of hard to see. What you can do is take your sphere, go to the object settings, viewport display, display as a wireframe. So now you can see that underneath we have a white mask. We could take our sphere, make it bigger, make it smaller, move it around, whatever we want. Here we have the ISO offset, so we can dilate our SDF or we can erode it. And then if you want, you can also invert the sign. This could be useful if you want to have like collision objects. Like let's say I want the smoke simulation to happen inside of this sphere. So right now with an inverted sign, everything's going to move around in the black area, but if it hits the white area, it's going to be a collision object. So that could be useful, inverting the sign. Let's make this smaller, and let's press play and see what happens. So obviously right now, nothing's happening because we don't have any forces or velocity in our sim, so let's add in initial velocity. To do this, I'm just going to get a vector node and do a vector pointing to the right, so 1 along the x. Let's plug it in and see what happens. And we start getting this crazy shit. And this is because when you create an initial velocity vector, you have to mask it using your source object. And I'll go more in depth about this later on when I talk about sourcing things properly. And it's going to make a lot more sense then. But for now, just do vector math, scale, and then plug in your object. And so now if you go back, press play, there you go. It moves correctly, although the smoke is very bright. And that's because on frame 1, we start with a density of 1. And then every frame, we add density to the simulation. So what you can do is on the outside of the node here, when you're visualizing the density, just do a math node and multiply it by, I don't know, 0.1. So there we go. Let's see how that looks. Yeah, much better. And there is your basic smoke simulation. When this reaches the edge, you're going to notice that it just kind of goes past. So what we can do is go to closed boundaries, and we can close it on the right side. Now it's going to interact with the wall as if it was a collision object, and then we can also close the top and the bottom and the left. Why not? Cool. So that's our very basic starting scene. So in part 2, I want to go over the advanced settings again, just so that you fully understand what all these settings do and how to use them to balance out speed and quality in your simulation. So the first thing I want to show you is actually not part of the advanced settings at all. It's just another node I've added to the Pyro Solver nodes node group, which is called Sharpen Attribute. And this is going to be a way of just quickly and easily adding sharper details to your sim, and you can just drop this after your after your output grid, and you can enable it by just turning on the on button, and you can see it's sharpening our detail. So you can do this not just for density, but for also color attribute or UV attribute, whatever you want, just by switching from float to vector and then typing in the name of the attribute. So if you're doing density, it's density in all small letters. If you're doing temperature, it's going to be temperature in all small letters. If you're doing color, it's going to be color in all small letters. Pressure, you're not going to want to, I mean, you could, I guess. You could sharpen the pressure. Velocity is going to be called vel if you wanted to sharpen the velocity field. And if you have plugged in custom, where's advanced attributes? If you have custom float attribute plugged in, you just type in the name. Let's call this custom. So up here, you would type in the name custom. So there you go. So in this case, we want to sharpen the density. So we type in the name density, and then this is the unsharp mask. So how far do we search for blurry artifacts? So if we increase this, we start searching further away. A value of 16 is usually good. If you have a lot of detail in your grid, you might want to crank it up to 32. And then this is the sharpen factor. So if we set it to 0, we have no sharpening. If we slowly increase it, we get more and more sharpening. And then if you go too high, it just starts looking a bit stupid. So that's the sharpen attribute node. Let's take a look at the advanced settings. So like I said, starting with the project non-divergence. So in a smoke simulation and fluid simulation, the whole point about smoke and fluid is that it's incompressible. So if you have too much smoke going into one area, it's going to push away from that area and just kind of flow away from it. And if you want to keep things really, really simple, really light, really fast, you can change this from 2 to 1. By the way, if you see an option, you don't know what it does, you can just hover over it and it'll give you a little description. It says how many times the velocity grid is corrected against divergence. So if we just do one time and I press play, you can see our simulation is running at 14 FPS, not too bad. And this is what our smoke looks like. Now if I go and take the pressure iterations down to, let's say, 4, look what happens. It doesn't look very good, right? So in real life, what would happen is the smoke would curl around, and this is because you have air over here and you have smoke being pushed towards the air. So you create pressure, and the pressure is going to push back on the smoke, which causes it to curl around. And if we don't have enough pressure iterations, we're not getting enough calculation to really figure that out. So you can crank it up to 32, so it's going to be a little bit better, but still not amazing. You can bring it up to 64, so it's going to be a bit better. Still not amazing. If you want, you can go up to 128. Okay, now we're starting to get good results, but slower simulation times. If you want, you can go up to 256. And then if you want, you can try and go up to 512, but what you might start noticing at 512 is that the smoke starts to do a little kind of jittery motion. Not sure if we're going to see any in this case, but it kind of jiggles around. Not sure why this happens, to be honest. But yeah, just don't really go up to 512. If you want really good quality, do 256. Otherwise, 128 is going to be plenty. Otherwise, the best option is just to have 64, but then increase the projection steps. Increasing the projection steps is overall going to be a lot better than just increasing the pressure iterations, which is why by default I have this at 64 and this is set to 2. In certain cases, you're going to see later on in this explainer video where we're doing certain effects, it makes a lot of sense to go up to 4 to really correct the fields from divergence. And so by having multiple divergence projection steps, you're going to detect collisions better, you're going to detect collisions with the walls better, so there you go. So right now I'll keep it at 2, and it looks good. Okay, so the next thing I want to show you is the advection methods. So you have velocity advection and field advection. The field advection takes care of advecting all fields like density, temperature, color, and then your custom fields as well. And velocity advection is just responsible for advecting the velocity, which is then used later to advect everything else. So that's why they're separate. So the most basic form, by the way, these drop-down menus, the top option is usually the worst, the bottom option is the best. So the top option is upwind. I'm just going to show you upwind for both. This is what upwind advection looks like. And I'll explain to you in a sec what it does. So upwind advection is the most simple way to advect things, or at least the easiest to understand, the most logical way of advecting attributes. And the way it works is if I take my grease pencil here, just demonstrate. So let's say that this grid is our smoke grid, and let's say we have a point over here, and this point has density and it has velocity pointing in this direction. So naturally, you're going to want to take this point with the density and then move it to over here where our velocity ends. And because this doesn't land on any specific grid point, it's going to distribute that density and the velocity to the nearby points. And so essentially what's happening is you're taking information from one point and then distributing to other points. And so you blur out the details. So you get blurry density, you get blurry velocity. And so overall you just get a blurry result, which is why this doesn't really look that good. And in addition to that, let's say you have a collision object here. You're moving it inside of a collision object and then advecting, and then later on in the simulation you're figuring out that, oh, actually we're inside a collision object, so let's just undo what we just did. So it's kind of just, it's not very good, right? So what we do, instead of doing upwind advection, is we do single stage advection, and this is like the most basic, the most kind of used advection method, I guess, in basic fluid and smoke simulation systems. If I select a single stage, let's go back, let's press play, see what it does. You can see now the smoke is a lot more kind of curly, and it's detecting pressure a lot better, and it's kind of preserving detail in the swirls and whatnot. So the way single stage works is instead of taking our attribute and moving it forward with the velocity, we're going to take our position and then subtract the velocity. So we look in the other direction, and then from here we're going to say what was the density at this point. So because this is not on a grid point, we're going to say what was the density here, 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 and here. We're going to find the averages and bring them to this point, and then we're going to take that point and move it back to our move it back to our original point, which is here. So instead of pushing things forward, we're looking backwards and saying what was it, and then take that and bring it forward. So computationally, this is exactly the same thing, because here what we're doing is we're doing position plus velocity, whereas over here we're doing position minus velocity. So between upwind advection and single stage advection, your simulation time is going to be pretty much exactly the same. What I'm trying to say here, by the way, guys, is that at the end of the day, you don't really want to be using you don't really want to be using upwind advection. The only reason I included it in this solver is because for educational purposes, if you want to mess around with it, go inside the node, see how it works. But yeah, I mean, in terms of simulation speed and power and quality, you don't really want to be using upwind. So then we have the next one, the best one, which is McCormack advection, and this is the method used by default in Houdini. Actually, not just in Houdini, it's also the default method in Mantaflow and in EmberGen and in pretty much every other new age smoke solver. The reason it's a big deal in my solver in GeoNodes is because it's the only solver at the moment in GeoNodes that has McCormack. Every other solver, Singa, VFX, and what was the other guy's name? Bad Normals and Sean Terrell, they all use a single stage. So if I just show you what McCormack does for field advection on its own, we go back, we press play, let's see what we get. First of all, you'll notice it's already slower, but also you'll notice that already our smoke is looking a lot more sharp, a lot more detailed. And this is because essentially what we're doing during McCormack advection is we are doing an unsharp mask correction. So kind of like this sharpen attribute node that I have. The way this sharpen attribute node works is it's doing an unsharp mask, and the way an unsharp mask works is it takes your current attribute, it blurs it out, it subtracts it from your original, which gives us the unsharp mask, which we can then multiply by the sharpened value, and then we add that back to our original value, which then gives us the sharpened result. So if that was a bit complicated for you, just chill. All right. But yeah, so with McCormack advection, let me just draw this to you in a visual manner. So we have our point, and the point velocity is pointing in this direction. But we're going to start by doing single stage advection. So we trace backwards what was the velocity over here, bring it forward. So now we've advected things forward. And then from here, we're going to do it in reverse. So we're going to take this point and then move it back to where it was. And so here, because we've gone forward and then backwards, now we have a slightly incorrect value, a slightly blurred value, because we advected it forward, changed it a bit, brought it back, changed it a bit. And so now that we have this blurry value, we can take our original value, so let's call it I don't know, D for density, minus AD for advected density, which gives us the error. Then we take that error and multiply it by 0.5. and then we can add that to our initial single stage advection. Let's call it a single stage, and that gives us core Mac advection, so sharper details. Let me just erase all this and go back to where we were. So we have sharper details, more detail than the density in the long run, so just overall a better smoke simulation. And if we do macro Mac advection for the velocity field, it means we're going to preserve detail in the velocity field, which means we're going to get more swirls, more vortices, more chaos in general as well. So if I just let this play out because it's a bit slow. Cool, so now you can see we're getting just a little bit more chaotic motion in our smoke. Just makes it a bit more natural, a bit more fluid-like. Alright, so those are the advection methods. Let's go over the trace modes. So by default, I've got trace midpoint, but if you want to keep things really simple, really light, you can do single step. So if I do single step right now, what you'll notice, hopefully, let me just emphasize a bit more by increasing my initial velocity maybe to 2. What you'll notice is that shit starts going crazy over here. And this is because of the core Mac advection. So when we do a velocity step that's way too big and we try and correct it, we're going to get like random errors and it's going to give you a lot of noise. And so what we can do to fix this is go to a more complex trace mode. So instead of doing single step, we can go one step up, which is trace midpoint. Let's see what that does to our smoke sim. And you can see that pretty much instantly corrects it. Still giving us a little bit of randomness, but in that case we can crank it up even higher. We can go all the way to trace RK4. Let's see what that does for us. Obviously at this point it's going to make our simulation a lot slower. We're down to 2 frames a second, but there you go, see a lot more stability. So having a higher order trace mode is going to make sure that you have more stability in fast moving areas. Now let me explain to you exactly what these trace modes do. So going back to our little grid representation, let's say we have a point over here, and let's say that the velocity in our fluid grid is kind of doing something like this. Let's say that the point here has velocity that's kind of pointing in this direction. So we trace backwards, so we do position minus velocity, so we look over here. And you can see that right now we're going to be transferring attributes from kind of the wrong place because our velocity is kind of curling around. So what we want to do, if we do trace midpoint, is instead of doing a full step back, we go backwards halfway, and then from here we look at the velocity field again. We say which way is the velocity going. From here we can see that the velocity is actually going in this direction. So then we take the velocity from here. That's what trace midpoint does. If you do trace RK3, it's going to be doing the same thing, but 3 times. So instead of going halfway, you go a third of the way. You look at the velocity. Velocity is going to tell you we're going over here. You look at the velocity from here. Again, it's going to tell you that we're going over here. So that's trace RK3. And then if you do trace RK4, it's going to be the same thing, but 4 times. Now, in Houdini, by default, they use trace adaptive, which is the best option because it'll automatically switch between single step, midpoint, RK3, and RK4, depending on how long the velocity is. So that's why you get the advect CFL. The CFL stands for how many grid points can the velocity pass before referencing the grid, the velocity grid again. So for example, if you have a point over here and the velocity is really, really long, you can see our CFL number is 1.5, so that's 1.5 grid points. So if we go past 1 grid point, 1.5 grid points, at this point we're going to look back at the velocity field and see if it's pointing in another direction, in which case we're going to change our trajectory and then go past another 1.5 grid points, look at the velocity again, go back another 1.5 grid points. So that's what trace adaptive does. Now, in a perfect world, trace adaptive would be the best option because it's adaptive, so you don't waste time doing RK4 for every step, and in small steps you can just do single step. But because of Blender's geometry nodes limitations, we couldn't really do, proper trace adaptive. So I had to find workarounds by using mix vectors and stuff like that, which makes it ultimately a bunch slower. So if I press play right now with trace adaptive, a CFL of 1.5, you can see we're down to 1 frame a second, which is just ridiculous. So again, I'm keeping this in the solver for educational purposes, but you shouldn't really be using it. If you want high quality trace mode, just go with trace RK4. You can see that's already bringing us up to 2.7 frames a second, despite the fact that it's doing 4 steps for every advection step. And if you want faster, you can go trace RK3 or trace midpoint, which is why I do trace midpoint by default. You can see now we're up to 4 frames a second. And if we do single step, we're up to 6, although we're getting errors. In that case, we could just change velocity advection to single stage. Let's see what that does for us. We're up to 7 frames a second. If we want, we can change field advection also to single stage, so that's going to be even faster. Now we're up to 11 frames a second. And if you want to make it even faster, you can also go to the attributes tab, and you have this option, disable temperature and disable color. Because in this case, we're doing very basic stuff. We're just simulating smoke with density. We're not sourcing any temperature. We're not sourcing any color. And so why would we waste time calculating temperature and color if we're not going to use it? So if you disable these two, watch what happens to our simulation time. Now we're up to 13 frames a second, 14 frames a second. And if you want it to be even faster, you can change the projectile divergence to have only one projection step. So now we are at 20 frames a second. So with the right kind of balance of settings, you can get pretty fast results with this solver. But if you want good quality, you'd crank up the projection steps, get a better collision detection. You'd change your advection method to Mac Core Mac to preserve detail. You'd crank up your trace mode to get better velocity flow, etc. So there you go. Those are the advanced settings. I think I covered everything here. One thing I didn't really cover was the custom float attribute and custom vector attribute. I'm going to cover the custom vector attribute later on in more detail when I talk about how to advect UV attributes. But for now, for the custom float, if I just enable this and I call this custom, and inside the source we can plug in something like, for example, a noise texture, like so. And then in the viewer node, instead of taking our density and visualizing it, we can just get a named attribute and type in the name custom. There it is, custom. Plug it in. And if I go back and press play, you have now noise. And you can see it's being advected by the smoke simulation. Okay, great. So let's go on to the next part. So in part 3, I'm going to show you how to create a wind tunnel simulation so we can take a look at the wind force and how we can source in, I don't know, collision objects and stuff like that, and we can look at creating different kinds of sources and yeah. So let me just start off by getting rid of this noise thing, disabling this custom thing that we're not using. We can keep these turned on because we're not going to be using temperature, we're not going to be using color. Let's just keep things really simple for now. Single stage. We'll keep this at trace midpoint just for good luck. 2 projection steps, 64 iterations, that's all good. And then we can go back to visualizing our density, and we can get rid of the initial velocity and just keep our main source. So let's go and duplicate our source object and put it maybe in the middle, something like that. And then we can duplicate our object to SDF, go and select this new object. Let's keep things organized. So this cube is our grid. We'll rename that to Pyro Solver. And then the sphere is our source, and then the second sphere is our collision. And so with the second sphere selected, we can plug it into the collision input. There we go. And let's go and add wind. So in the forces tab, wind. So you'll notice buoyancy is grayed out. And again, that's because we turned off temperature. So if you turn off temperature, suddenly the temperature gets grayed out and the buoyancy gets grayed out. Same thing with the color. It's grayed out because disable color. So wind. Enable wind. By default, it's going to be going along the x-axis, and here you have the strength and then the turn speed and join speed. Let's just see what that gives us. So you can see we're getting an error here, and this is because we have closed boundaries. So if we have closed boundaries, where is the wind coming from, right? So you're going to get an error. So let's go to the closed boundaries and open at least the left and the right. So that's going to allow wind to flow through. There we go. And there you go, we have a very basic wind tunnel simulation. So what we can do in a case like this is maybe adjust our grid size so that we have something a bit longer, so we can do 2 by 1 and 200 by 100, and then have a subdivide mesh node just waiting so that if we want higher resolution, we can do that. Let's go back and let's see, this is fine. That's fine. Maybe make this a bit smaller and make this a bit smaller. Can also get rid of our viewport overlays here. Let's also actually hide our collision object and our source object. Okay, so we have this basic setup. Nothing much going on. If I increase the subdivision, something I haven't mentioned yet, although you probably already know it, but you'll notice that we can actually see our velocity steps. You can see really, really big steps. If I increase the wind strength to, let's say, I don't know, 2. Let's go back, let's press play. We have even bigger steps. And if I keep things really basic in the advanced settings, so single stage, let's do single step, and 1 projection step, look how our smoke reacts with our collision object. You can see it's just barely getting by. That's because our velocity is so big. So if we do 2 projection steps, already we're going to start detecting the collision a lot better. So we're going to get more smoke flowing around it. So that's already a bit better. Then you can see here, because we have such fast moving velocity, we are taking massive steps. So we're kind of losing details. So that's why having a higher order trace mode, let's do trace RK3, would be better. So that's already looking way better. And then if you want to preserve some detail in there, you can do matte core, matte convection. So we're kind of sharpening details. But still, we're left with this problem of having these massive steps, these massive kind of circles moving forward. And that's why you'd go all the way to the top of the simulation node and increase the substeps. If we do 3 substeps, we're going to have 3 circles between each circle to kind of blend that detail in there. Obviously, it's going to be 3 times slower to simulate, but you can see, yeah, we're having a much smoother transition here. And obviously, with smaller steps, with more substeps, means we have smaller steps. We're going to have much more accurate motion over here. One very important thing to keep in mind about substeps is that the more substeps you have, the more advection steps you have. And the more advection steps you have, the more your smoke sim is going to become blurry, right? Because naturally, every time you advect an attribute forward, you kind of lose a little bit of detail. So we can try and, counteract that by having higher orders of velocity advection and field advection methods. But still, you're going to be blurring out details a little bit. So if you increase the substeps, you're going to be blurring out some details a little bit. So just be mindful of that. You want to keep your substeps as low as possible without sacrificing quality. So anyway, let's bring that back down to 1, and let's do something a bit more creative with this. Instead of just having a sphere as our source, let's delete this and then create, for example, another UV sphere. And then let's just do an array modifier, maybe pointing down. And we'll do like 7 and then scale that down. Just move that over here. And we can do select that. And so now if we go back, we press play, let's see what we get. Let's take the wind strength down a little bit, maybe 1.5. And then that's fine. These settings are fine. I'll just change that to single stage. Cool, so there you go. That's pretty cool. Massive velocity steps. It probably would be worth having just an extra substep in there. What you might notice is that at the start of the simulation, the smoke looks kind of bright, and at the end, it's looking a little bit dark. That's because I forgot to mention that by default, if you go to the simulation tab under shaping, you're going to have dissipation, a little bit of dissipation on. So that's going to make the smoke disappear. If I have dissipation at 0.1, and I press play, see the smoke disappears a lot faster. If I set it to 0, it means we're always going to have smoke in our simulation. So that's going to help things already a little bit. By the way, another thing I forgot to mention is vortex confinement. Let's just quickly go over that. So if you go to the simulation tab, here you have viscosity. By the way, viscosity doesn't work super well. If I just turn that on, let's do 6. You'll see what that does. Just kind of makes our smoke simulation really boring. So yeah, there's not really much use case for viscosity at the moment. Anyway, then we have, so vortex confinement, which in other words is vorticity. So if we enable this and we do a strength of, 2, watch what happens to our smoke simulation. See, now we have kind of extra vorticity in our smoke simulation, which makes it a lot more interesting. And you'll notice it doesn't make a huge difference on the performance. So without vortex confinement, we're simulating at 12 frames a second. And if we enable vortex confinement, we're at 12 frames a second. So really, I mean, pretty much no computational time extra, but we're getting so much more detail in our smoke. It's kind of like a cheap wave mimicking Mac velocity advection, right? So if I do Mac velocity and density, we're down to 5 frames a second. And Mac is going to really give us, more detail in the swirls and the vorticity. So it's going to give us a better looking sim. But if you don't want to, go all the way down to 5 frames a second, you can just keep things at single stage, and then do vortex confinement, which is still going to give you a pretty swirly, pretty turbulent looking smoke sim, but with a much better performance. And if you want, you can combine that. So we have vortex confinement, single stage for velocity, but then we sharpen details with Mac Core Mac. So you get like a kind of in between. So you get yeah, 8 frames a second, not too bad. And by the way, if you want to make things colorful as well, you can take your density, multiply it down, and then run it through a ramp. And in the color ramp, we can do something like a black to, I don't know, red to yellow to white, maybe to black again. And we're not seeing anything right now. That's because our viewer is set to view a float attribute. So just Control Shift click on the color ramp twice, and there you go. Now it's working a lot better. And we can also, if you want, maybe set this to B-spline or something. Give ourselves a little bit of threshold, and then if you just multiply your value up a little bit more, you get some funky details in there. Maybe that's too much. Yeah, I think that's too much. So now we're going into part 4 of this explainer video where I'll show you how to properly source attributes. Like I said, I want this to be kind of clear to you guys because it gets a little complex if you want multiple sources. Each of them have their own initial velocity, each of them have their own color, etc. Okay, so with our current setup, let's make sure everything's as simple as possible. We'll have no vortex confinement, 2 projection steps, we'll do trace midpoint, single stage, single stage. So right now we have one source object. Let's get rid of the collision object. We have one source object with initial velocity going into the initial velocity. So if we press play, we get this. Simple, easy. What if we wanted another collision object, another source object over here? So let's duplicate this, move it over to the right, and we're gonna have to do the object to SDF, select our source object. So what if we want to add that into the density? Well, you add it, so math, add. So now we have a second source. If we go back, there you go, you can see both of them are red. And what if we want the initial velocity of this one to be going in the opposite direction? So first we create another vector going in the opposite direction, so -1. And then we scale it by our second source. So we do vector math, take in the vector, scale it by the second source. And then to add that in, you just do a vector math, add. And we can add it in, and now you're going to have 2 sources with both their own initial velocities. Pretty nice. So, and let's just add vortex confinement to that, because why not? Because it's cool. We'll do 1.5. Much better. All right, so what about sourcing color? All right, so first of all, for sourcing color, we're going to be viewing color. So let's get all this, get rid of it, view color. So again, you can just do Control Shift click until you get the input for color, just to make sure that we have that color input. Just do that because it's cleaner. And to sourcing color, it's exactly the same thing. So let's take this, move it over. Let's create a color node. The one on the left, I want it to be red. So let's make this, we'll just make it all the way red. And let's plug that in to the color. And you can see that that should work, although it's not working. Oh yeah, lol, because attributes disabled color. So let's enable that again. So now we have just red everywhere. So what we need to do is vector math, because a color is basically just a vector. So vector math, scale it by your source. So this is the left source, plug it in. So now we're only doing color on the left side. And then if we do our second color, let's make it blue. And then do a vector math, take in the blue color and scale it by our second source. And we're going to add that with a vector math add. So now we have 2 sources, each of them with their own velocity, each of them with their own color. And looking pretty good. So the smoke actually, right now, looks a bit shit. The colors look really, really bright and really washed out. What I recommend you do if you are using color is just do a vector math and scale it using your density attribute. And that's going to make things a bit more dramatic, and we can just multiply the density down before we do that as well. There we go. So we can take the density multiplied by like 0.1, maybe 0.2. I will do 0.15, and there you go. So now you have a bit more kind of detail in your color. And again, if you combine that with a sharpen attribute, we can sharpen the density field, which should sharpen the mask. So if we enable that, yeah, we get a bit more detail. You could also try doing a sharpen vector and type in color. So that also kind of works if we can crank up the sharpen and see what that does. That kind of works. Otherwise, yeah, we can just keep it at float and sharpen the density and crank up the sharpen strength, and there you go. So here we are, basic setup. And pressure, if I just get rid of initial velocity and I plug the source into the pressure, you'll see what that does. It will start to inflate our source object. And because we have a closed boundary here, it's kind of pushing away from it. And if we combine that with initial velocity as well, we kind of, so this is without pressure. And then if I go and plug the pressure in while it's simulating, you can see that we kind of inflate the smoke a little bit. So we add kind of more volume to the smoke. That's what pressure does. So I guess you can kind of get creative with this. I don't know, you could try plugging in noise here or something. I don't know what it might do to your simulation. That's for you to experiment with. And then finally, last but not least, the source velocity tab. So this is when things get a little bit more complex. So at the moment, if I just do my source object as density and I press play, we don't have any motion. If I take my object and I move it while it's simulating, you can see there's no motion at all. If I want to bring over that velocity, the motion from my object, what you have to do is first of all enable source velocity, and then anything you plug into this collection. So let's create a collection. Let's call this initial velocity. I know I didn't spell it right, but whatever. Take your source object, put it in the collection, and then select the collection, initial velocity. And this is your velocity scale multiplier. So right now, let's just see what it looks like with a value of 1. So if I press play and I start moving my object around, you can see we're kind of getting velocity transfer onto our grid. Not looking amazing. Let's try cranking up the velocity scale to 5 and see what we get. Yeah, so that's a lot better. So it does look a little bit noisy, and that's because the method I'm using here is I'm storing the position attribute of the points on the object. The reason I'm doing position instead of location is because if we have another object, let's say for example, let's say I have a cube, and let's just bring it down here and source the cube, and then take the cube and do object settings, display as a wireframe. We go back. So we have this cube. If I move it around, by the way, notice these weird streaks that are appearing. That's actually pretty cool. Looks like radioactivity in a cloud chamber. But the reason these streaks are happening is because our cube object is too sharp. It has 2 sharp edges. So what we need to do is go modifier and remesh it. So we have something with a bit more detail. We can go even lower voxel size to 1.05. And then we can do a smooth modifier. And so what that's going to do is it's going to just make sure that the edges of our cube are slightly rounded. So if we do like a factor of 1 and a repeat of maybe 8, that's too much. We can do 4. But so just by adding more detail to the mesh and smoothing it out a little bit, what we get is a smoother mesh, which means we're not going to get those artifacts anymore. So now if we go view this, make this a bit smaller, you can see that I can move this around and we're not going to get any of those errors anymore. But so another thing we have now with this method of sourcing velocity is that I can take the cube and rotate it, and that's also going to give us motion, which is cool. So that's something that we didn't really have before. So you can have rotating objects and moving objects. I don't know why it's freaking out so much right now. Let's see. Yeah, I don't know what's bugging. It feels a bit slow. But there you go. So that's initial velocity. And if you want as well, you can have so now if I take this cube collision object and I move it around, you can see that we're kind of transferring velocity from our cube on the smoke as well. Kind of looks like it's going in the wrong direction. But whatever. You get the idea. So part 5, we're going to look at temperature and buoyancy. Like I said earlier, this is kind of the most boring part of the explainer video, but you kind of have to know what these settings do if you're not already familiar with them. So let's go. I'm going to set up a very similar scene to what we have here, except I'll do it the other way. So we'll do 1 by 2, so 100 by 200, so we have space for the smoke to rise. I'm going to keep it basic level, and no initial velocity, and no collisions. Let's get rid of the collisions. Turn off source velocities, and then just take our sphere, put it down here. So if we press play, what happens? Nothing. Let's make sure our boundaries are closed, and then let's go and make sure that our temperature is enabled. And let's plug in our source object as a temperature source. And what that's going to do is it's going to create heat in our simulation, which is going to make the smoke rise. There you go. So if we go now to the simulation tab, if we go to the forces tab, we have the buoyancy tab, and here you can control the direction that the smoke is going to flow in if it has temperature. So if you hover over this option, you don't know what it does. It'll say the direction that the smoke will flow when it has temperature. So right now it's going up along the Y. Let's turn that to 0 and then maybe do 1 along the X, and you'll see that now the smoke is going to go to the right when it has temperature. There you go. Let's keep that at up, and let's increase the strength. So you see if we increase the strength, the smoke is going to go up even faster. If we take the strength down, the smoke is going to go up slower. I don't know why that seems so bright as well. Anyway, that's pretty much buoyancy for you. But then we have the simulation settings, the shaping settings. So we already went over dissipation. If I have dissipation, I'll do 0.1. The smoke disappears pretty quick. If we take dissipation off, we don't have any dissipation, so the smoke stays in our scene forever. If we have cooling rate is the same thing as dissipation, but for the temperature field. So if we have no cooling rate, it means the smoke is always going to be hot, so it's always going to be going up. So when it goes up here, it bounces and comes back down here, but then because the smoke is still hot, it's going to keep falling back up. So if we have a lot of cooling rate, let's do 0.1, it's going to go up, but then as it goes up, it's going to slow down because it cools down. And then when it reaches the top, it's going to kind of bounce off the ceiling, curl around, and then that's it. It's just going to flow around, but it's not going to keep going up. You know what I mean? So that's the cooling rate. Let's bring it down. And then the temperature diffusion is how much the heat or the temperature spreads out. So what we can do is we can actually visualize the temperature field here, plug it in. This is the temperature field. And then if we increase the temperature diffusion, you can see that the temperature gets kind of blurred out. That's what temperature diffusion does. So what does that actually do to our density field? Well, you're going to see in a sec. It makes it a lot more kind of wispy and smooth. It makes it a little bit boring. So there you go. So another effect I was playing with earlier that I want to show you guys with temperature is the Rayleigh-Taylor instability effect, which was originally shown in one of the Tagma tutorials for Houdini. And now that we actually have my Pyro Solver, we can actually do this in Blender. And yep, it's pretty cool. So to do this effect, let's start off by creating our grid. So it'll be 2 by 2, 256 by 256. And then no subdivisions, we'll keep that off for now. Let's plug that in as our grid. One substep, let's just get rid of our sources here. Let's turn off dissipation, turn off temperature diffusion, turn off cooling. And this is important because later we're going to source temperature, and if these things are on, it's not really going to work. So turn all of that off. Viscosity off, confinement off for now, but we're going to turn it on later. We don't have any collisions in our scene. We're not sourcing any velocity. We don't have any wind, no turbulence, no drag, closed boundaries. And in the advanced tab, we disable color because we're not using it. We don't need these. This is fine, although I'm going to change these later. Trace midpoint, single stage, single stage. Okay, so we have this, and we don't need a source because we're going to be creating our sources procedurally. So what I want to do is, first of all, separate this grid in top and bottom. So we can do position, separate it into XYZ, and then get the Y value. So if we plug the Y value into the output, we get this. And so if we just say if the Y position is greater than 0, there you go, it's going to be masked. So we can use that now as a switch. Let's do a switch float. We take in the greater than. If the business is true and you left your mom's in the hood.
Because if the business is true that you left your mom's in the hood,
then the value is going to be 1. So what I want to do is use this kind of mask to tell Blender that the bottom of this grid, I want it to have temperature. I want it to have a temperature of 1. So I want the smoke to rise, right? Because our buoyancy, wherever it is, our buoyancy tells us that if we have temperature, our smoke is going to go up along the y-axis. So I want this bottom half to be white. So let's do 1 and 0. But at the top, I don't just want it to have no temperature. I want it to have negative pressure. So I want this to go down. I want this to go up. So it's going to be 1 and -1. And that's going to go in as our temperature. Now, as the density, we can just do this, but inverted. So we'll just do this switch, but we'll have -1 and 1. And let's visualize our density. Now, another thing is, if I press play right now, we're going to be constantly sourcing density and temperature into our simulation. So I only want the density to be sourced on frame 1, and I only want the temperature to be sourced on frame 1. So I'm going to multiply these inputs. So multiply density, multiply temperature. If the scene time, the frame number, if the frame number is less than, let's do frame, if it's less than 2, then we multiply. So in other words, if the frame number is less than 2, so in other words, frame 1, then multiply the density by 1 and multiply the temperature by 1. Otherwise, multiply by 0, which means we only get sources sourced on frame 1. And you can see that nothing is really happening. And so what we can do to make this a bit more interesting is take our temperature field, which is going in here, and multiply it with a little bit of noise. And that's going to give us a little bit of randomness. So just do a math multiply, get a noise texture, plug it in, and we can do a noise of, let's do 6 with a detail of 8 and a roughness of, I don't know, 0.6. And so let's see if that does anything for us. And you can see now we're starting to get some motion in our smoke, some drippiness. Wonderful. So I'll just go and crank the multiply value up to 1 because we don't have any recurring density sources, so that should be better. Also, another thing we should do in a case like this, because we have like 2 sections of our smoke kind of pressing against each other, which is creating a lot of pressure. So what we should do is go to the advanced tab, project non-divergence, maybe crank that up to 128, or just straight up go for projection iterations, which should help already a lot as well. Another thing we can do is add vortex confinement, which will just give us a bit more of an interesting result. Not sure why it looks like things are kind of fading out. Let's see, shaping. This is all off. Okay. Anyway, another thing we can do is just make sure to do a higher level. Let's do trace RK3 and matte core matte convection, And another thing we can do as well is multiply our temperature by, let's say, 5. So it's going to be even more fast. Again, I don't know why it's looking so contrasted. It looks like I have a sharpen attribute enabled, but I actually don't, so not sure what's going on. But anyway, if you set this up properly, we could do, a subdivide mesh, give it a bit more quality, and then if you let that simulate out, what you get is this. So now in part 6, we're going to go over particle advection. So if you want to create a smoke sim and then use that smoke sim to push points around on a grid, let's go over how to do that. Because it's 1 by 2, we'll do 100 by 200. And then we'll create a source object, just a sphere. Do an obj to SDF. Select the object, plug it in as the density. Let's get an initial velocity vector pointing up along the y. Let's get a vector math. Scale the vector by our source object. Plug it in. See what we get. Okay, let's run through some settings. One substep, this is all fine. Collisions are off. Source velocity is off. Shaping, these are all off. This is off. We can keep vortex confinement, because why not? Buoyancy, wind, turbulence, drag, close boundaries. Let's disable temperature since we're not using it. And let's do 2 projection iterations and trace midpoint. And let's just do matte core mac for the density field, in fact, and keep this at single stage. And since let's multiply that down. There we go. So this is the current state of our smoke simulation with vortex confinement. looking a little bit blurry up here. Maybe it's worth doing Mac velocity detection. Let's see. Okay, so it just looks a little bit more interesting now. Cool. So let's create a particle simulation from this now. So let's say I want to take my initial grid. So I'm going to take my grid and I'm going to convert it into points. So we can do mesh to points. Now I don't want to turn everything into points because right now, let's just unplug the viewer node. Let's just delete the viewer node. So if I turn everything into points, we get this. I only want to convert points that are inside my source object into points. So we can just take our source object and plug it into the selection. So now we only get points inside our selection. Take the radius down. Let's do like a 0.01 maybe. And let's hide our sphere. There we go. And then with these points, what we want to do is plug them into a simulation zone. And in the simulation zone, of course, we want to offset the points. So set position, and the offset is going to be the velocity of the grid. Now, if you just do this, it's not going to work because this is a surface and these are points. And so we need to transfer the attribute from our surface to our points. So we use a node called sample nearest surface. We take in the grid, we take in the attribute that we want to sample, which is a vector. And then the sample position is going to be just a position node. And then we can plug that into the offset. And so now we should get motion. Let's see. There you go. So the problem is that we just have points and they start moving. We want to constantly emit points. So instead of plugging these points into the simulation zone, let's join them into the simulation zone. And now we have this. Wonderful. We can take the radius down, make it a bit smaller. If you want more resolution, you can subdivide your grid so you get more points. If you want more kind of random distribution of points, instead of doing a mesh 2 points, you can do a distribute points on faces. Plug that in here. And then the selection, again, is going to be our object. The density is going to be something ridiculous. 1,000. Let's do 10,000. And then the seed, we can just use the scene time, frame number. And let's do a set point radius and scale these points down to 0.005. See what we get. There we go. So additionally, instead of having this, you could just have, for example, get rid of this join. So we just have a grid of points that we source on frame 1, not inside our collision, our selection. Do a set point radius, or actually, yeah, we'll do it like this. 0.005. Let's crank up that point count. Let's do 0.003. And if you press play, you can see now we have that motion in there. So what you'll notice is that we're kind of getting these empty spaces because all the points kind of converge to the nearest velocity. So to randomize that a bit, what you can do is take the velocity vector that you're using in the set position and just do a vector math and scale it with a random value. And then we can do the minimum because we don't want it to be all the way 0. But we can do like 0.7. And so that should give us a little bit more randomness. So we kind of fill in the gaps a little bit better. By the way, I know the quality of this video isn't great, and this is because I'm currently remotely connected to another computer, which is more powerful, just so I can run these visualizations faster for you. Because if I was doing this on my laptop, it would be pretty slow. Yeah, I forgot to mention that this Pyro Solver just doesn't really work well on laptops. You kind of need a good PC with a good CPU. If you're doing this on a laptop CPU just isn't really powerful enough to get fast calculations. It's gonna be a lot slower on a CPU, on a laptop compared to a PC. So there you go. And if you want to add color to that, you know, we could just take the sampled velocity and then just do a vector math and calculate the length, and then multiply that by a multiplication value, and then run it through a ramp. And we can say the ramp goes from black to blue to turquoise to white, and we can plug that into a viewer node. There we go, and we can just increase that multiply. Something like that. So now we have this. Okay, so now for part 7, I'm going to show you how to advect a UV attribute using the 2D Pyro Solver and using the custom vector attribute input. So let's just keep the setup we had earlier because, well, because it's basic and because it works. We have this basic simulation. You can see it's pretty low res. And what I want to do is advect an image texture using a UV attribute. So first of all, I have to create a UV attribute. So to do that, what we can do is just get the position coordinate and separate it into X, Y, Z. And then if we just do a map range, we can properly get our attributes in. So we can get the, because this goes negative 0.5, so the X value is going to go from negative 0.5 to positive 0.5. And how do I know it's 0.5? Well, because our maximum grid size along the X is 1, so half of 1 is 0.5, so negative 0.5, positive 0.5, and here it's 2, so it's going to be positive 1, negative 1. You could also just use the bounding box node, plug in your geo, separate it into XYZ, get the minimums. But yeah, I'll just do position, separate into XYZ from negative 0.5 to positive 0.5, and then for the Y, we're going to do from negative 1 to 1, and then we can combine that into XYZ. So this is the X, this is the Y, and that gives us a UV attribute. So if I just plug that vector into the output, you get a UV attribute. And then we can plug that into the advanced tab attribute custom vector, enable it, and then we can just call this, for example, UV map, or just call it UV, or my underscore UV, just to show you that we're actually creating our own attribute here. Plug it in, make sure it's enabled, and if we go back, we press play. I'm not seeing anything. That's because we're visualizing the attribute before the simulation. So just take a named attribute node, and then type in the name of your attribute. What was it? My UV, which is a vector. Plug it in. Let's go back. Let's press play. And there you go. You can see we are advecting the UV attribute. And if you want, you can sharpen that attribute. So if we just do a sharpen attribute, and we turn it on, and we set it to vector, and we type in my underscore UV, we're sharpening the UV attribute. I'm just going to ignore that for a sec. So now we have this UV attribute. We can go and assign a material. So let's just do a set material node. And we don't need this viewer anymore. I don't think we need this either. So we just have our grid. We can create a new material. Material 1, select material 1. Let's go to EV, viewport, shaded, shader editor. And then we can get our attribute node and type in the name. So my underscore UV, plug in the vector. Let's see if that gives us something. There you go. And so now we can get an image texture. Let's just go and find an image texture. So I've got this this wood texture from Grayscale Gorilla. And you can see with no UVs, it doesn't know what to do. So we plug in our UV. And you can see that it is affecting our simulation. And if you want to resize the UV because I don't know you're not happy with this projection, you can do a vector math. Set it to multiply. Set it to 1, 1, 1. Let's say I want the entire thing to be a bit smaller, so I can do 2, 2, 2. And now you can see our entire texture is smaller. And if I want it to be kind of stretched, you can stretch it. So it's like 1, 2, 2. And you see, even though we stretched it and scaled it, our advection still works perfectly. So like this, we have like a really detailed smoke motion without having to have a really detailed mesh. Our grid is, pretty low level. So there you go. That's advecting UVs with the custom vector attribute. And finally, for part 8, the part you've all been waiting for, the velocity field trickery. So this is going to be a bit more complex. So brace yourselves because it means having to go inside the node and do a few changes, but you can do a lot of really cool stuff with this. So for this effect, I really want to start off from complete scratch, just so we're all kind of clear about everything that I'm doing. So once again, I'm appending the nodes. There we go, done. And then I create an object and I split the view. And I go to GeoNodes, new node tree, replace it with a grid, replace it with the Pyro Solver, plug it in. plug it in. And let's get our grid to 2 by 2, 256, 256. Shit. That's not 256. I was afraid that my computer was gonna blow up. I hate that. All right, now let's get a source object. So in this case, I'll just do the same thing I did in my video. So I'll do a text, wherever the hell that is, text. And let's just do the letter S. And let's change the font because that is nasty font. I think I did Arial regular. Yeah, why not? Could do Arial bold, but whatever. Okay, so we have this text, and we need it to be three-dimensional. So let's first of all convert this from a font. So object, convert to mesh, tab into edit mode, extrude it, and we'll just recalculate normals for good luck, and then we can do F3 geometry to origin. And then because we have all these sharp edges, it's probably going to be a good idea to remesh the S. Let's do a smaller voxel size, smooth shading, why not? And I think that should be fine. And let's scale it up so it kind of fits our screen a bit better. I should have used the other font, whatever. The bold font, whatever. This is fine for explanation purposes. Let's hide the text and let's continue on our GeoNodes grid. Let's get obj to SDF. Select our text objects, plug it in as the density. And then let's get a viewer node, view the density, view our grid, which gives us this. And let's make this a bit more interesting by multiplying some noise. So let's just do a math and multiply. Let's get a noise texture, and we can make this noise texture interesting by changing it to rigid multifractal, doing a detail of 7, a roughness of 0.6, and a gain of 50. And then getting the position attribute, plugging it in so we have like a kind of texture coordinate in there. And then we can do a mix vector, duplicate our noise texture, plug in position, plug in the factor as the second input, and then change this to 4-dimensional. So now you get something a bit more interesting. And if you want, you can also just run it through a math node set to power. Let's do a power of, I don't know, 2. It's a bit better. And we can do another multiply and just crank it up to, I don't know, 2 as well. And if you press play, we're going to keep adding density to our simulation every frame. So once again, we'll just do scene time and then frame number if the frame number is less than 2. So now we have density on frame 1, and then that's it. And then it's slowly going to fade away because by default we have simulation, shaping, dissipation. Let's go turn dissipation off, temperature diffusion off, cooling rate off. This is off. Collisions we don't have. Viscosity we don't have. Confinement we don't have. Forces we don't have. Closed boundaries, let's enable all of that. And then in the advanced tab, let's just make sure we disable temperature because we're not going to need it. Color, we're not going to need it. We don't care about these. So we are going to be increasing the projection steps, but I'll do that later. And then trace modes, these are fine. And then these advection modes are fine for now. So to get that kind of trippy effect, what we need to do is first of all up res because 256 is not going to be enough. And let's also just multiply our density because it's kind of hard to see it right now. There we go. So inside the Pyro Solver, if you press tab, I know this gets a little scary. These are just your output attributes. These are this is the group input node. Over here you have some basic stuff. So we calculate the point separation, we store the near points index numbers, and we calculate the CFL number. This is the PS core. So any node that belongs inside the Pyro Solver, it starts with the abbreviation PS. So Pyro Solver, store near points, Pyro Solver, calculate point separation, Pyro Solver, CFL. And so this is the Pyro Solver core. And if you select this, press tab to go inside, you can see the inside of the Pyro Solver. And you'll notice that I have OCD and it looks fucking beautiful. Everything's organized perfectly. Everything's framed. Everything's labeled. CFL set collision velocity, project non-divergence, PS project non-divergence. Just everything's just wonderful. So again, just to show you the kind of complexity of some of the things happening inside these solvers, this is the the Pyro Solver advect Mac core Mac vector. So if I go inside here, because it's a vector, you can only do it, well, you could do it as a vector, but it's better to do it as individual floats, so you separate them, and this is what the inside of a Mac core Mac advection step looks like. So it's pretty complex. And you also have like extra node groups in here doing more stuff. So yeah. Anyway, at the beginning of this simulation loop, I left you guys a little space. And if you go to this little space, you can just do shift, right click and drag to do a little cutout, and then we can do a store named attribute, because what we're going to do here is we're going to override the velocity attribute. So store named attribute, velocity is a vector, and in my Pyro Solver, velocity is called vel. And then for the value here, just for now, just do a vector, doesn't matter, just plug it in, and then we can take these two nodes and press Control G to turn it into a group node. And so now we're inside this group node, and let's just press tab to get out of here to make sure this is wired up nicely, and we can rename this custom vel field. All right, so to get the effect we're looking for, by the way, something I forgot to mention as well is if you're inside the Pyro Solver, you can't view the Pyro Solver. So what you can do is split the view, and in this view, you can press tab, click on your group input, press tab, click on the group input and press tab. So we're back to the main Pyro Solver level, pin this window, and then view the viewer. So now you can actually see what we're doing. And at the same time, we can go and work inside of our custom vel field. So go inside here, and then here you can create a vector pointing in whatever direction you want. So let's say the vector is pointing to the right, so we do 1, and that's going to freak the simulation out. So then what we do is we do vector math, scale it by the density field. So named attribute, and get the density, which for some reason isn't showing up, so just type it in manually, density. And that's going to do a little something. Let's press play, see what happens. There you go. So you can see just by doing that, you can already see we're getting this really cool kind of result. So right now it doesn't look amazing, and that's because we have really basic advection settings. So let's do 4 projection iterations, which is already going to correct buildup of pressure a lot better. So we're going to get more kind of tendrils in here. Also, since we have a quite fast moving smoke on the first few frames, it's probably a good idea to do maybe trace RK3, maybe trace RK4. If you want the best quality, again, just go with trace RK4. And then if you want sharper details, Mac Core Mac. And if you want to preserve detail in the velocity field, Mac Core Mac. I'll just keep things fast and simple. I'll keep this at single stage. Let's see what that gives us. And that's already looking really cool. Now, what you might notice with these settings is that it's looking pretty turbulent, and one way to fix that is to actually just add a little bit of viscosity. So just enable viscosity. A viscosity of 1, I think, should be enough, really, for most cases. That should kind of smooth things out a bit. Also, inside the custom velocity field, if you plan on having multiple substeps, it's also going to be a good idea to take your vector and multiply it by an attribute called dt, which is delta time. So if you have multiple substeps, it just makes sure not to increase the scale every time. Now, this velocity vector, instead of just having it going in one direction, let's have a vector pointing away from the center. So if you don't know how to do that with vector math, it's pretty easy. You just do vector math, subtract. If you want to get something to point in the direction of something else, you do vector math, subtract. And the first input is going to be the thing you're pointing towards. So if I want to point away from the center is going to be the second input. So the first input is going to be the position attribute. So it means we're pointing away from the center. And because the velocity vectors are going to be shorter from the center and longer away from the center, what you should do here as well is normalize. So just normalize this, and let's see what that does. There you go. So now you have that effect that we had from the video. Really cool. And if it's still too strong for you, I mean, you could do another vector math and scale it down by, I don't know, 0.5. There we go. And another thing I did in my version as well is, oh yeah, I also added noise. So we have the position minus, so we get a vector pointing away, we normalize it, and then we can add, so vector math, add, get a noise texture, and you can just turn off normalize, so it'll make it 3-dimensional noise, plug in the color, Might also be a good idea to normalize the noise just in case. And then we could do a scale, vector math scale. We could scale it by, I don't know, 1.5. Maybe do like a scale of, I don't know, 3. So that's going to add a little bit of random motion in here. Maybe that's too much. That's probably too much. Let's take it to 4 and then do a scale of 1. Okay, so another thing I did in my version is I actually had a little bit of dissipation. So think about it like this, right? Because we're creating this velocity vector and then we're scaling it by the density. If we have dissipation, so the smoke starts to disappear, it means the smoke is going to move slower and slower. So if we do a little bit of dissipation, let's do 0.006. I think I had something like that. It means the velocity starts off fast, but then kind of slows down a bit. Cool. And so if you want to do what I did with the pulsing effect, you can just find a way to keyframe your input. So instead of doing frame number is less than 2, you can just do a we can do a switch float. So if the switch is turned on, we're using our source, and so on frame 1 we can have it enabled, and then keyframe the switch. So just hover over, press I, and then go to frame 2. Go to frame 2, turn it off, keyframe. Then you can just skip over to I don't know, let's say frame 60. Keyframe it at 0. Go next frame, turn it on, keyframe, go next frame, turn it off. Oh, sorry, turn it off, keyframe. And then we can duplicate those keyframes, Shift D, and then move them over to, I don't know, 120. So if we go back, and if you were to increase the resolution here, and if we did, I don't know, Mac Core Mac velocity advection, and add a little bit of vortex confinement, 0.5 or something. Let's see what that gives us. So there you go. You have that kind of second pulse. Now if I just play that back real time. It's a bit chaotic, but it works. So there you have it. And if you really kind of mess around with the that velocity field, you can do some creative stuff. If you create like some symmetrical kind of velocity fields, you can kind of get stuff like this. And so in this case, I'm also kind of converting the density into a height map. I'll show you how to do that real quick. So let's just go back and find a cool looking frame. Like this is kind of cool, I guess. And then on the outside of the Pyro Solver here, we can just take the grid and run it through a set position. So we take the grid, we do set position, and in the offset we do a combine XYZ, and we use our density as the Z value. Let's just take it down. And then I forgot to, yeah, we can do a viewer node. Why not? And it's not working. I think it's because we actually need a group output first. So there we go. Now you have this kind of displacement map thing. And you see we have some really high peaks over there and then some really low lows. To kind of balance it out, you could do math, set it to power, and do a power of 0.5 or something. So that's going to flatten things out a bit, and then you can do another multiply. Or actually just take this one down to, I don't know, 0.2. And a set shade smooth. Maybe take the exponent down some more. And if you want like extra detail, I guess you could do like a subdivision surface maybe. And maybe another set position and a blur attribute, and get the position attribute and just blur it out. And so you kind of smooth it out a bit with like 4 iterations or something. So there you go. Now you can kind of turn it into like a height map. And then if you like apply some shaders to that, and then we can just get the geometry, I guess, position, and then separate it into XYZ, and then use the Z, which is the height, and then run it through a ramp and kind of clip the whites there. And yeah, you can get some kind of interesting looking stuff. Run that through a second ramp where you can add some color. You can do like black to let's do B spline. Well, actually, let's do yeah, B spline. something like that. And then we could do like a little, I don't know, greenish color or something. So there you go. Now you kind of have this 3D effect if we plug that into the color of the principled shader. And then you can set the roughness to whatever you want, and then do a little bit of subsurface. So we can do subsurface random walk, radius of 111, and then bring the weight up, and then take the scale up as well. With EV, it's not going to be super obvious, but yeah, you can get some decent looking stuff there. All right, so that's it. Hopefully, you guys can do some cool stuff with this. Otherwise, I'll see you in the next one.